Should we get started?
Yeah, I think it's probably a good time.
Okay. Good morning, everybody. My name is Mehdi Moradi. I'm an associate professor at Computing and Software and a co-host of AI in Healthcare Rounds. On behalf of Marnix Heersink School of Biomedical Innovation and Entrepreneurship, I want to welcome you to today's AI in Healthcare Rounds. The purpose of AI in Healthcare Rounds is to explore the latest advancements and applications of artificial intelligence and its transformative impact on healthcare and innovation. I encourage you to participate actively and join the conversation and ask questions throughout the presentation. Today, we are pleased to introduce Dr. Jeremy Petch to give the rounds. Dr. Petch is the Director of Health Innovation at Hamilton Health Sciences and an assistant professor at the Institute for Health Policy Management and Evaluation at University of Toronto and the Division of Cardiology at McMaster University. He's the founder of CREATE, Center for Data Science and Digital Health, a multidisciplinary research and innovative team with expertise in health system operations, data engineering, data science, software engineering, and interoperability. Prior to joining HHS, he led St. Michael's Hospital transformation into a data-driven organization through deployment of an advanced data analytics infrastructure and co-founding the Heersink Center for Healthcare Analytics Research and Training, which is home to a team of data scientists with a specialization in machine learning, simulation, modeling, and natural language processing. Dr. Petch was a core member of CarDIA-AI Health Technology Expert Review Panel from 2015 to 21 and co-lead of Digital Health Secretariat of the Hamilton, Ontario Health Team from 2019 to 22. And he's also a collaborator of mine in our research and a supporter of the kind of work that we do in AI in healthcare. So I'm very pleased to welcome him. And we are looking forward to your talk, Jeremy.
Thanks so much for having me. So I believe to share my screen, I'll just need to bring down the current slide. And while we're doing that and just switching screens, I also just wanted to mention that we're being joined by my long-term collaborator on this work, JD Schwalm, who's zooming in from Ottawa and in the middle of a conference there, but he will pipe in at certain points if there's any questions around the kind of the clinical dimensions or things best spoken to. JD's an interventional cardiologist at Hamilton General Hospital, as well as associate professor at McMaster and a scientist at the Population Health Research Institute. So just to set the stage for a moment, CREATE, which some of you will have heard of, but some of you will have not, we founded CREATE to accelerate the pace of digital and AI innovation in the healthcare system. And we're actually embedded fully at Hamilton Health Sciences, and working within a research hospital network really provides a rich collaborative environment and a living lab to test and scale innovations. And that's actually a picture of JD in the cath lab, and just having access to work directly with clinicians and actually test out these AI solutions in a clinical environment is really an invaluable opportunity and something that's not open to a lot of purely university-based scientists or private industry. And so we're very privileged to have the relationship with HHS. CREATE has two components. The first is our digital health team, and they specialize in the design, development, and deployment of novel clinical applications. And our second team is our data science and engineering team, really our kind of skunkworks R&D group that focus on machine learning and a clinical artificial intelligence, as well as kind of managing the kind of classic big data. And often these two teams, especially in the case I'm going to present today, actually work collaboratively, where they're developing a novel digital health solution that has AI components built into it to provide things like clinical decision support. This is just an important thing about kind of the perspective that CREATE brings to all of our innovation work, is that we're very much guided by the quintuple aim, which will be very familiar to those of you with a health sciences background, maybe less familiar to those that trained in computer science or engineering, but it's this idea that innovation in healthcare should be simultaneously trying to improve population health or improve outcomes, lower or improve the efficiency of healthcare and lowering healthcare costs, advancing health equity, while simultaneously also improving both clinician experience and patient experience. And this is something we try, a lens that we bring to all of the types of projects that we bring or that are brought to us and try and only select those that have the most impact across all 5 of these dimensions. And I'll talk a little bit later about how this project aligns very, very well with the quintuple aim. Also, just a useful bit of context to understand kind of where CREATE sits, because the world of AI and the world of AI, even the world of AI in health is actually pretty big. And I think it's helpful to kind of come back to a traditional framework in the health sciences of thinking about basic research, translational research, and clinical research. So in traditional health sciences, basic research really kind of focuses on biological systems, big picture questions about what causes disease. Translational researchers are focused on understanding how biological knowledge could actually be translated into potentially treatments for disease, and clinical research, which is really looking at moving that towards the bedside and evaluating which treatments are actually safe and effective in humans. And I think a parallel can be drawn to the work that we do in artificial intelligence. There's an enormous amount of basic research that has taken place, and actually a lot of the focus over the last, say, 40 years in AI has really been in basic research. How can computers perform functions that were traditionally performed by humans? Then there's been tremendous amounts of translational research over the last 20 years around how can those general advances in AI actually be adopted to the biological and health system domains? How can they be made to work with healthcare data types? How do you go from being able to recognize images of cats and dogs to being able to spot tumors on an MRI? And then clinical research, which is, can AI be safely and effectively used to actually manage specific diseases? And this is really where CREATE spends our time. And we're taking often algorithms that have been developed by translational researchers. Sometimes we're doing a little translational research ourselves, but most often we're using those algorithms as novel tools with which to model healthcare problems, generate things like risk prediction scores, which can then be applied directly in the clinic and evaluated clinically. So I'm going to give an example of one of these clinical AI projects today, which is the CarDIA-AI project, which is around using AI to improve outcomes and reduce costs of cardiac investigation. So I need to start out by telling you a little bit about cardiac investigation today. So this is an image here of an invasive coronary angiogram, and which I'm just going to call ICA from here on in. So ICA has long been the gold standard to diagnose coronary artery disease, and it's essential to facilitate life-saving revascularization when it is applied to the right patients, patients with obstructive disease who would in fact benefit from revascularization. The trouble is that for some patients who receive an angiogram, we realize that that their disease is non-obstructive, or they may in fact have completely normal anatomy. And in those cases, their cardiac conditions are going to be managed medically, right, with medications, not through something more surgical like revascularization. So the trouble is that when we apply invasive coronary angiogram, which is deeply invasive, right, we're inserting a catheter up through the arteries and into the heart and injecting with dye and taking an image. When that's applied to a suboptimal population, the population that has normal anatomy or non-obstructive disease, it increases cost to the system while simultaneously carrying a small but real risk to patients. About 1 out of 1,000 patients at least that undergoes an invasive coronary angiogram will have a bad outcome, and a fairly serious bad outcome, stroke, MI, or death. And so it's not a procedure we want to do on patients who don't absolutely need it, who don't stand to benefit from the revascularization. And this problem is actually not a small problem. When you look across Ontario, and this is data from all of Ontario, the purple bar there is the Ontario average. All the turquoise bars there are different cardiac centers across Ontario. About 40% of coronary angiograms in the elective patients do not have significant coronary artery disease, do not have obstructive disease. And when that actually number approaches about 60 to 70%, when we really start to look at the low to moderate risk patients. So there are a lot of patients for whom we are putting through a risky procedure and an expensive procedure that potentially don't actually need that procedure. And this has actually been called out by the Auditor General of Ontario. This is actually a live policy issue in Ontario right now, because the Auditor General has noted that we are not making the optimal, currently in Ontario, we're not making optimal use of available technologies through which to diagnose coronary artery disease. And in fact, they've in their response to the Auditor General, the Core Health, now part of Ontario Health, has actually called out the work that JD Schwalm was leading at the time, and now we're working on together as it's one of its primary policy responses to trying to improve this in Ontario. So just to give you a sense of again, the magnitude here at our local centers and just the current flow of patients through the healthcare system. So if we're just going to take, we do a couple thousand of these on elective outpatients every year, but just to kind of make it easy to wrap our heads around. So imagine for every 100 patients. So currently, if a community cardiologist identifies that they're a patient's at risk of coronary artery disease, they'll send a referral to our triage unit at the Hamilton General Hospital. And that patient will be triaged for urgency, right? Like, how is this patient super sick? Do they need their angiogram right away, or can they go a little bit later? But all of these patients ultimately are going to receive an invasive coronary angiogram. And as you can see there, about 56 out of 100, 56% of those patients may benefit from revascularization. But fully 44%, so 44 out of 100 of those patients, are exposed to the risk of the procedure with no benefit of revascularization. So to add on to this problem, what we've come to realize is that there's also a sex-based inequity within this current practice. So as we started to perform subgroup analysis, we found that women, while they made up 40% of the elective outpatients who are undergoing invasive coronary angiogram, what we realized is that women who were undergoing ICA were actually 40% less likely to be diagnosed with obstructive coronary artery disease than males. And what that means is that women are currently being exposed to the risks of ICA with a much lower chance of therapeutic benefit than men. And this is a real problem within our system, and almost certainly rooted in historic patterns with respect to men being enrolled in clinical trials in cardiology at a much higher rate than women. And so all of our risk scores and things like that have been based on sort of biased data. But this is what we see in our current data set. So what is the alternative to invasive coronary angiogram? There is an evidence-based alternative, and it's cardiac CT angiogram, which I'm just going to call CCTA from here on. And it's been established in clinical trials to be effectively equivalent to ICA in the right patient population for diagnosing coronary artery disease, but it is significantly less expensive and it is lower risk. The trouble is, you would think, well, why don't we just give everybody a CCTA? Wouldn't that be better? The trouble is that CCTA first strategies introduce kind of the converse problem to the one we're trying to solve, which is that then you have 56% of patients that underwent a CCTA potentially unnecessarily because they're going to be found to have obstructive disease and they're going to need to be re-referred for invasive coronary angiography so that they can benefit from revascularization. So, and you don't want to, in addition to just the medical waste that's associated with that, there's also the exposure to an unnecessary dose of radiation. It's not huge, but that's still, we want to try and minimize exposure to radiation wherever we can. So ideally, we would have a model of care that can optimize patient selection for CCTA versus ICA. Now, JD has been working on this problem since at least 2018 when he launched the CarDIA study in partnership with a number of other cardiologists at the Hamilton General Hospital and the Niagara Health System. And what they were trialing was a centralized triage system for ICA and CCTA, because one of the challenges right now is that community cardiologists would need to decide which of these two technologies were appropriate for their patient, and they don't have a good screening tool to do that. But even if they did, they would have to figure out, do I send this patient over to radiology for a CT scan, or do I send them for invasive cardiology for an ICA? And so JD's team studied a centralized triage model for both of these two diagnostic tests, where eligible patients would be referred for ICA, but would then be identified and given a CCTA first if that appeared to be the most appropriate test for them. And they did this through a manual chart review, which was definitely not scalable, but they were trying to prove the concept of whether a centralized triage model could work. And in fact, they showed that it absolutely can dramatically reduce the number of ICAs that are done on patients with normal anatomy or non-obstructive disease. So they have a model of care that works. The challenge they were facing is that it's not necessarily scalable because it was so heavily dependent on manual review, which is very time consuming, and they were focused on the most low-risk patients. They weren't necessarily going to be well set up to identify those patients who were a little bit more complicated to figure out if they were going to be more appropriate for one test or the other. And that's when JD and I started working together, and he was curious whether we could use AI to help with this patient selection problem. Because what they were really missing, as I said, was a scalable method for screening for these two patient populations. So the CarDIA team partnered with Create, and what we did was we trained an AI model on 12 years of HHS referral data to predict which patients would benefit from which tests. And what we found is when we applied machine learning to this problem, we were able to achieve a very good discriminatory performance, far outperforming any previous model. And so what we're looking at now is this, and this is a combination of the model of care that JD's team developed while incorporating the AI screening tool. And this will give you a sense of the projected magnitude of benefit we would achieve. This is so we took the AUC, we used some fancy math and did some recap, something called a net reclassification index in order to go from a predictive score to understanding what the real world impact would be. And this is sort of the result here. So you can see that what we're imagining is a model of care where community cardiologists identify that there's a risk of CAD, and they send a referral to the centralized triage unit that JD's team developed during the CarDIA study. At that point, the patient would be screened by the AI tool using the patient's medical history to either receive CCTA or ICA. And the patients that receive CCTA, you can see there, many of those patients will get a diagnosis of normal or non-obstructive disease. And those patients will have they will avoid an angiogram and thus just be managed medically. A certain number of patients will be found on CCTA to have a risk of significant or obstructive disease. There's no model is perfect. AI is smart, it's not that smart. It's definitely not perfect. So a small number of those patients will be found to have a risk of significant CAD, and they'll rejoin the pool of patients who were predicted to go directly to ICA. And those patients will go ahead and have their invasive coronary angiogram. About, again, 56% of those patients will benefit from revascularization, and we get down to only 14% of patients who will actually be exposed to the risk of procedure with no benefit of revascularization. So that is a 30 out of 100 patients who will now be correctly diagnosed through CCTA. So we go from 44 out of 100 patients who are under experiencing the risk without the benefit down to only 14. So that is in medicine is a very large effect size. And this is just a picture of the tool that we have developed to put out in front of the AI model, because AI models aren't particularly interesting to look at. They're just a whole bunch of code. But in order to deploy this, we built out a software tool, a computerized clinical decision support tool. So it is able to ingest the data of a patient's medical history, either through a direct connection to a hospital information system or through fields that can be filled in for reasons I'm going to explain in a few minutes. We've opted to do at this stage, we're filling in these fields manually to maximize our data quality. And based on that, it provides a recommendation for a clinician review. And in this case, you can see that the recommendation is for CCTA, and noting that the probability of obstructive disease is only 32%. Therefore, that we've, based on where we set our decision threshold, we've determined this patient should go to CCTA. And then the tool displays, and I've cut off the list, it's a much longer list than this, but for ease of clinician review, you can see a list of all of that patient's parameters that you're used in the decision, so that if the clinician is concerned in any way about the recommendation produced by the AI tool, they have some transparency and ease of review. So what's the potential impact of this combined AI-based clinical decision support tool with a centralized triage model for clinical deployment? The first is reduce risk to patients by decreasing the number of unnecessary ICAs performed. So that we're estimating based on our reclassification index and looking at the numbers we're expecting every year, we're estimated to avoid 1 stroke, MI, or death per year in the HHS and Niagara Health systems. We are looking at cost savings. So I mentioned before the cost differential. An ICA costs nearly $1,600 for every procedure. A CCTA costs only $600. And so even when we count up that small number of double tests that would occur, people that would get CCTA but be found to have obstructive disease, we're looking at, and this is a fairly conservative number, at least $600,000 in savings to Hamilton Health Sciences and Niagara Health every year. And if you think about scaling that up to the province of Ontario or scaling it up to Canada, those numbers start to get quite large. And we look to be able to address gender inequity in cardiac investigation. And we can get into the weeds if you'd like during the question and answer, but what we found is that because of how we trained the model on objective clinical features rather than on labels that could have in some way been socially mediated, we were actually able to develop a model that performs equally well for men and women, which should be able to eliminate the gender inequities that we described earlier. So just thinking about this, kind of coming back to the quintuple aim, which I think is really important for when you're thinking about, when to use AI in a clinical context. We try to only use it when we think it can meaningfully advance the quintuple aim. And in this case, we think it's very much aligned. We believe we will improve population health by reducing critical adverse events. We'll lower cost of care by reducing the cost of cardiac investigation. We will be able to address gender inequity that's associated with traditional cardiac screening. We'll be able to improve clinician experience by reducing the moral distress associated with iatrogenic effects, with those bad outcomes that happen to some patients that get unnecessary ICAs. And we will also be able to improve patient experience because there's significantly less discomfort associated with CCTAs. And so this is to give you a sense of this journey that we have taken, because I think a lot of sort of AI studies get published and they're like, oh, it's problem solved. I published my modeling study. I've solved this whole healthcare problem. But that is not kind of really the true journey that you need to take when you're going all the way from kind of problem definition through to fully validated solution. And so this work, as I said, began in 2018 with JD's CarDIA study, really around, I've split retrospective validation implementation research on this diagram. So really leading with implementation research, understanding the clinical problem and beginning with clinical pathway design at the beginning so that we actually had a place to locate an AI decision tool where it could have impact. We then moved to retrospective validation, and with the publication of our machine learning model, validated on local historical data, which was published in 2021. We conducted a silent trial of this tool. So that's where you actually deploy an AI tool in a real clinical environment, but you don't make any decisions based on the tool. You just let it run in real time, record the predictions, and then compare its predictions with ground truth, which was the ICAs. And that way you can actually confirm that your tool works as well in the real world as it worked in the lab on retrospective data, once you're actually faced with all the messiness of real world challenges like missingness in the data and other things. And then we are also in the midst of preparing to publish our work on the external retrospective validation, where we got access to data from the 18 other cath labs in Ontario through a relationship with ICES. And so we're also confirming that this doesn't just work on the our local data here in Hamilton and Niagara, but in fact, that the model is generalizable to the population of Ontario. And as I'm going to discuss in just a moment, we are now moving into the clinical outcome evaluation, because one of the things that has been observed by anyone that's following the clinical AI literature is there's actually been quite a few clinical AI products that got to the randomized control trial stage. And even though their models worked extremely well on retrospective data, once they actually tried to measure their impact on clinical outcomes, quite a number of those trials have been negative for a whole variety of reasons. So one of the things that's really critical for us is proving that this really works in the real world on real clinical outcomes. And so we have, I'm happy to report, won 2 grants to support the CarDIA-AI RCT, as well as a budget impact study to help with the Ontario policymaking question. So this is the design of the CarDIA-AI randomized control trial. So this is a combination of the 2 diagrams you have already seen, where we will be randomizing patients to either usual care in the control arm or to our experimental arm, where they will be screened using our AI tool to receive either invasive coronary angiogram or cardiac CT. And so the trial details, this will be an open label, multi-site, patient-level randomized control trial. Given the magnitude of the effect size that you saw earlier, we will only need to randomize 114 patients, or 57 patients per arm. The primary outcome we're looking at is the rate of normal or non-obstructive coronary artery disease that's diagnosed through ICA. So we're looking at the decrease in normals diagnosed through ICA. And secondary outcomes include budget impact of a new strategy for risk stratification of CAD in low-risk patients, and the difference in the rate of normal or non-obstructive CAD diagnosed through ICA between males and females. So equity is a key outcome metric for us for this RCT. And finally, just to kind of conclude with some thoughts on the challenges and barriers to doing this kind of clinical AI work. There's been quite a few. We encountered some really huge challenges relating to data drift that resulted from a mid-study structural change to the way that CoreHealth actually collects data from the 20 cardiac centers. They made major changes to their database, major changes to the data that they actually required. We are very much at the whim of provincial policymakers. And this meant that when we went to run our silent trial, we went to update the model with sort of the most recent data, all of the data structures had changed. And that required kind of a complete reworking of the model and the tool that we had been using. And yeah, it was just a testament to some of the things that can get in the way when you suddenly try and do this stuff, data-driven work in the real world, and all the databases change. We also faced some really interesting challenges around adapting a model developed on cross-sectional administrative data to a longitudinal clinical environment. And this is something I've encountered throughout my career, which is you get these data sets from various clinical problems, and they're sort of presented to you as sort of cross-sectional, and you're told, oh yeah, all this data is going to be available to you at the time of prediction, all be great. And then you actually get into the real clinical environment, you start using the tool, and you're like, there's a lot of data that doesn't seem available when we suddenly need it. And you start to uncover things like, oh yeah, it turns out the weight and the height, you don't usually get that until the anesthesia consult. And oh yeah, no, it's true. Some patients do show up without a creatinine, and then we just have to repeat it on the day of the experiment. Like, well, that's not going to be available at the time when we need to actually do this screening. And so it required reworking of the models, as well as working with the clinical team to see, are there ways that we could get some of this data at the time of prediction to try and maintain the highest possible model performance. So just this gap between kind of what you see when you get provided with a training data set and actually what happens when you actually go and try and work within a real clinical environment. Relating to that is the realities of clinician use of EHRs. And so while the data that ultimately goes to the CoreHealth registry is very clean, it's only cleaned because there's a group of very hardworking clerks in the heart investigation unit who are making sure that the data that's submitted to our provincial authority is of high quality. But what we've realized is with the use of hospital EHRs, often a lot of data is missing earlier in the process before those clerks actually get to do their work. And that's the reason why we pivoted away from using our integration to Epic and just using that data the clinicians were implementing to actually trying to use more of a manual data input at this stage of the randomized control trial to ensure that we're actually getting the high quality data into the predictive model rather than getting garbage in and garbage out. And that's obviously, for those of you who are thinking about it, that speaks to the question of scalability long term and the need for us to then go back to our clinicians that are part of the cardiology group and see if we can improve processes around getting higher quality data into Epic earlier in the process. So really thinking about kind of the change management elements of trying to do AI effectively at the bedside. Another important thing to consider is just the limited current capacity of CCTA. One of the main reasons why we don't use CCTA for everyone at the moment is we actually have very limited imaging capacity in Ontario and really across Canada. And that means there's just not a whole bunch of free CCTA slots just sitting around. And in fact, JD's really has done tremendous work to engage radiology and others in actually generating the capacity we need to run these pilot studies. But part of our work with Core Health, the provincial stakeholder, is around helping understand if a model like this was to be as effective as we think it's going to be in the real world, how much additional CCTA capacity would need to be added to the province of Ontario to actually be able to do something effective with this AI model. Another important consideration is the limited data on race and ethnicity that we collect in Canada, and certainly that we collect here in Ontario. And that limits our ability to analyze potential model bias, which is, I'm sure all of you are aware that fairness in AI is a really important subject. We've already called out gender bias as a problem with current models that our model is able to actually overcome. It's possible that our model was able to also overcome any potential racial or ethnic imbalance that there might be because of how we trained it, but we're not able to confirm that because of the lack of data in Ontario. Our key strategy around addressing this is external validation, paying particular attention to communities and cardiac centers such as Sir William Osler in Brampton, where the local ethnic makeup is very different from Hamilton and Niagara. So we'll pay particular attention to that while we're writing up the external validation manuscript. But it's important to call out and be transparent about potential limitations, and this is one we have our eye on. And the other important thing, and this is kind of a to be done, and any statisticians in the room, feel free to contact me afterwards if you have interesting ideas about this. But one of the things we've been thinking about a lot in AI implementations is how to handle post-implementation distribution shifts, right? Where it's possible that clinician behavior could change in some important and unknown way in relation to our model. Like in response to the fact that we're now doing this model, the community cardiologists start to get responses. When they send a patient for cardiac investigation, they're starting to get their patients back having gotten a CCTA rather than an ICA. Is it possible that those clinicians will change their behavior in some important way? We don't know, but that's something we need to have our eye on and be paying attention to, because if clinician behavior changes, that could actually change the sort of distribution that our model is expecting or challenge our model's assumptions in some currently unknown way that's important to keep our eyes. So just some sense of the kind of challenges and barriers that we've faced as we've done this work. And so just a few papers of interest for anybody that wants to go deeper on this, my contact information. I realize this is probably a much less technical talk from a AI perspective, though I'm happy to get into those details if folks would like, than they might be used to or thinking about. But what we found is that it's not that there aren't technical challenges or to do with sort of approaches to machine learning with this, but we find that the importance of paying attention to kind of things that many of you from a health science background will think of as like clinical epidemiological challenges, I find are just as important and take up just as much or more of our time sometimes than some of the ML methodology challenges when dealing with one of these highly integrated clinical AI projects. So I hope it was interest, and happy to turn it over to questions now.
Thank you very much, Dr. Petch. This was really good. From personal experience, I agree with you with that on that last point. So I have some thoughts and questions, but let's go to the audience first. So if you have a question, can you turn on your camera or at least raise the hand so I know to go to you? There is a raise hand option on Zoom. Then we know you have a question. We have both Jeremy and JD that can answer on technical and clinical side of this. So this is an opportunity. So feel free to ask questions. Just if I'm missing somebody trying to ask a question, just go on mute and start talking and we'll hear you.
I have a question. This is Maddie.
Go ahead.
So considering the AI here, did it increase the sensitivity and specificity of the CCTA or did not affect it?
That's a good question, and I may pass it over to JD here. But what we see is the purpose of the AI here isn't, we're not modifying or doing anything with the CCTA itself. Rather, we're using it to optimize patient selection for one modality versus the other. So the challenge right now is we don't know which patients are going to be the right patients for which test, and that's all we're using the AI for. JD, do you want to add anything to that?
Yeah, and I think we try to pick patients. Part of the eligibility screening is picking patients that will have a high quality study, which is most important because we don't want to send these patients off to get the CCTA done. Ends up being poor quality due to several factors that we know can put them at risk for that. So that's part of the screening. So again, that will improve the both the sensitivity and specificity of the actual CCTAs on the patients that are referred to that.
Thanks for that, JD. I think examples, if I recall incorrectly, are things like AFib, right? So a patient with atrial fibrillation, very unlikely to get a good CCTA. And so we've actually just taken those patients out through our exclusion criteria. And so ideally, the sensitivity and specificity of CCTA stays high.
Great.
That's really great talk. Really enjoyed that, and really interesting to see what you guys are working on, Jeremy. So thank you for sharing that. I just had a quick question just about the data to train it, and in radiology, it's often hard to get the data cleaned and kind of de-identified and all that. Now, I understand you guys had a unique database from 2 centers and lots of data in there, but did you have to go through a big process of kind of validating the data? Was it all kind of pre-populated fields from which you could pull data, or was there prose where you had to process the language? Just curious to learn a bit more about how you guys dealt with that.
Sure. I mean, JD, do you want to speak a little bit to the Core Health database, its origin, and then I can talk a little bit about kind of pre-processing and that kind of stuff?
Sure. So essentially, the Core Health database, which was originally the CCN database, was used to look at wait times for people getting access to invasive procedures and devices across the province. And so it was an administrative data set that was there to ensure that people were triaged in a timely fashion so that regardless of where you lived in the province, you got access to these investigations in a similar time frame. So that's where it kind of was founded. It's been around for decades, and it's been used and validated in multiple studies in the world of cardiology, particularly around acute myocardial infarctions, the management, and so on, and it's been published and used quite a bit. We have access to our own data, so all centers have access to their own data to evaluate for quality purposes, anything along those lines. So those are some of the kind of basic questions about the actual data set itself.
Yeah, and because, as JD says, because this was originally developed as kind of a quality improvement database, the data was fully identified. So one of the first things we had to do to get access to the database was figure out a way where we were going to be able to have the people that have access to it, like the people in the cardiology lab, get it over to us for R&D purposes, while preserving some data that we needed for linkages. So what we wound up doing is they did have to strip out a bunch of fields, but we really wanted to be able to link to the Ontario Marginalization Index to get ourselves some sense of social determinants for these patients, because we felt that there was a good chance that some of those were going to be important predictors. And so we actually had to write like a shell script, which we sent over to them that actually de-identified the data, but also did a linkage between the Ontario Marginalization Index was embedded in the script. They executed it. It linked to the 6-digit postal code, and put in all of the social determinants data, and then stripped out the postal code so that it couldn't be used to re-identify the data. And then that was sent over to us. So there was a bit of to do about that. And then I think the data that we got was really high quality, right? It was like registry quality data. The level of missingness was near non-existent, which of course sounds too good to be true. And this is sort of what I was alluding to earlier, which is that what we discovered later at the time of clinical deployment was that that data was like a bit of a moving target. Like at the very beginning, at the point of triage, a lot of that data was there, but it turned out a bunch of data was also missing. And what we were getting was the perfectly cleaned data after the patient had even received their angiogram. The last few data elements were imputed, or not imputed, but inputted by the staff into that, and that's what we had been getting. And the trouble with that was not all that data was going to be available when we have to make the prediction. And so it took some clinical process mapping to actually understand when was the data, and then we actually had to kind of either in some cases retrain the model without some of those data elements that we would have loved to have had that would have boosted performance, but just weren't going to be available because they weren't going to be available. And then some others that are available a lot of the time, but for a handful of patients, they're going to be missing, in which case we had to develop imputation strategies around some of those. So hopefully that gives you it was a bit of a mixed bag.
Yeah, it's good. It's just great. It's an opportunistic data set in many ways that's well primed for this type of research. And, it just makes me wonder, like, if you can link it with the ICS databases, there's so many things you could potentially, associations and things you could look at. So kudos to you guys. Well done. It's very, very fascinating.
Thanks, Christian. Yeah, it's such an interesting point about the ICES because we have been working with the full data set at ICS, and it's so tempting. Like they've offered us, like, do you want us to link to this data set? And we could link to the community health survey. We could do this and we could do this. And it's like, that stuff all sounds really cool. The problem is we're going to get a model that can never be deployed in the real world because it's dependent on all these data sets that aren't available at the time of prediction in the cath lab. And so we've actually had to say no to a bunch of that stuff, even though it would make for awesome academic papers, it wouldn't make for a deployable clinical model. So it's been a neat give or take and a bit of a journey for us as we sort of think through some of these deployment dimensions.
Great. I want to get something quick in also. I was curious about the validation. You have this validation chart. I really like the way you have systematically shown that. One thing that always kind of like becomes an issue, and I agree with you 100% that sometimes your institutional validation, what you call silent study, which is really good way of describing it, running the model, but not making any clinical decisions on that basis. And you get some results from that. But you also mentioned the need to do this externally. And I want to understand what changes between two. Why is that the results of the model change? I can think of, for example, having different scanners. If you're looking at radiology in general, different scanners in different institutions or different protocols of imaging and things like that. So what else is there, or is that a valid reason?
That's an awesome question, Mehdi. So in this case, and JD, feel free to jump in, but I think there's two things that clearly vary when we look at the 20 cardiac centers across Ontario. The first is the ethnic and racial makeup across Ontario. So here in Hamilton and Niagara, people of color make up like 5% of the population. But then if you go to Brampton, people of color make up like 30% of the population. So the chance of us, there's a real chance of bias that's race or ethnicity related that could have crept in. So that's one thing. The other is physician behavior, and I'm talking about the referring physician. So one thing I didn't mention, because it's a short talk, but one of the things that's interesting was we included the referring physician as a predictor variable. So we were actually able to model historic referral patterns, because what we learned is there are some clinicians who do a great job of only sending really sick patients for ICA. Like they seem to just be very good at spotting the patients with obstructive disease. They send them for ICA. There appear to be some other clinicians who send let's just say a wider variety of patients in for invasive disease. And those patients, many of them turn out to have non-obstructive disease. And the machine learning model was able to model that and account for it in its prediction such that referring physician is one of the top predictors in the model. And so this is why I'm sure you're getting why distribution shift is potentially such a major problem over time for us to keep our eye on. But also, in order to validate and have it be deployable, we would actually need to train on the provincial data. So we want to check just how well does the model function when it doesn't have available data for referring physician, and then we'll obviously retrain the model once it's been externally validated for the whole province so that we've modeled referral patterns across the whole province. But those are at least two reasons that I can think of. JD, others to add?
I think the one other point would be is that we do a lot of vetting of our data before, as Jeremy mentioned, before it is uploaded to the provincial site. And there can be variability across the cardiac centers in how well that's done. And so while the whole overall data set has been validated and used in other studies, it's still going to be useful to see how does the data behave at each one of these individual sites, given the vetting may be somewhat different across the board.
That's right. Yeah, some concern about how good is the ground truth really at some of these other sites, right?
The end result's always the truth, as we at least know from the reporting, but what data goes into it. Yeah.
And are there more questions from the audience? I don't hear anything, so I do one quick more question. And I might be phrasing this incorrectly for the type of a study you're running, but you are essentially suggesting that some of the patients that would have gone through certain study, maybe they didn't need that, right? That's essentially what we are doing. And so far, from what I understand, we have not really used that in real world to say, don't do it, because we are still doing different kinds of studies on it. But in any of these studies, did we also look at the possibility of recommending that we don't do the angiography and later realizing that it was actually important to do the angiography? Meaning, are there any false, in this case, I don't know if call it false positive or false negative, but are there any false positives here in assuming that positive meaning no need for the procedure? Are there any false positives in the work?
It's a good question. We can say, at least from the CarDIA trial that we did in the original run, we had one patient that went through a CCTA, and this was the real world kind of evaluation where their calcium score was 0, which suggests that they don't have any significant coronary artery disease, and they were deemed to have no significant plaque. That eventually were found to have a plaque on cath as they came back in through the system. And when it was looked in hindsight, that was one patient out of the 256 I think we had run through the model. That's the real world experience, and I think that still demonstrates it's quite a safe study or safe procedure. We know that when we look at the evidence with CCTA done in the right patients, it's just as accurate as coronary angiogram, so there shouldn't be any of these concerns. Maybe I'm misunderstanding your question, but that is
no, I think that was good. That was what I was looking for. But in this case, the CCTA still can, so the patient can still be sent to angiography. Like they essentially, the harm to the patient is to get one additional study, essentially, right? Right. Okay.
Yeah.
So basically, we're trying to fix a situation where currently everyone's getting the invasive study.
No, I get it.
The alternative to everyone does CCTA, but then 56 get the ICA. We're trying to optimize. You're totally right. From what we can tell, the only real risk involved with this study is that a small number of patients will receive 2 tests instead of 1 test. Small number, but that will be much smaller than either of the harms associated with the other 2 models. So we're moving to what we hope is an optimal.
Got it. Yeah, that's exactly what it is. Great. Any other questions? I see a hand. Go ahead, Franca.
Hi, I just wanted to ask a piece about scalability. I know that you had mentioned it earlier. And so in terms of the EHR systems, and so you had mentioned Epic, would you see like moving forward any compatibility with strictly Epic, or how do you see this working on larger, like various platforms? I don't know if you can speak on that.
No, it's a great question. So we've thought about it a lot. And when we think about Ontario, which would be the next logical place to try to scale, and certainly the provincial policymakers are interested in this approach, there would be an opportunity to actually integrate the tool into the core health portal itself. So right now, my understanding, correct me if I'm wrong, JD, is that when a patient is referred for cath, their data starts to get entered into the core health portal where we actually pulled this data from. And there's a triage recommendation that comes back from core health for each patient. And that would be an obvious time to also, in addition to the triage recommendation, to also have the AI model recommendation provided back to the patients. And that could, or provide back to the cath lab. So that would provide the obvious path to scalability in Ontario, because it doesn't require integration with Epic or Cerner, because those both, and probably Meditech, like I'm pretty sure we'd need to integrate with all three if we try to do EHR app. So that's the path in Ontario, but that's Ontario only. Everywhere else is a different approach. So we're looking ultimately, when we go to make this software tool available after the trial, assuming the trial is positive, we're not trying to make money off this. We'll almost certainly open as an open source tool. And what we're probably going to do is create integration connectors for Cerner, Epic, Meditech, as well as the manual option that we're going to use during the trial. And all of those will be options for people that want to make use of the tool. So that's kind of our current thinking.
Sounds good. Thank you.
Thank you. I have one more, I think. Madi, did you ask your question, or is this a new one? Go ahead if you have a
new one. It's just a quick comment, because I heard earlier you mentioned that the good physician who most of their referral is almost like 80% of coronary artery disease when they come to our center. But I'm afraid, I know with experience it gets better and better, but sometimes it's the other way, like it has the other side, so you might missing a lot of patients where you miss the medical and cultural intervention to treat the disease earlier. Thank you.
Yeah, that's a very good point, Maddie. I mean, I think there's the happy medium in between. I mean, if you have somebody who's referring and all of their patients have severe disease, they're probably missing a lot in their practice and they're not getting appropriately referred, versus the patient who's sending all of their normal patients. They're probably, or have the vast majority of normal, they're probably sending too many patients for invasive. So there is a happy medium. We don't know what that exact number is, but we know the pendulum's too far over right now, and we want to try to fix that. But that's a very good point.
Samir, go ahead.
Yeah, thanks for a very interesting talk. I'm an internist at Health Sciences. There's outline is what are the possible outcomes that a patient does not test? Like, are you seeing some referral? Sometimes we send people for cath who, probably could get a test or potentially no test. Would that be a possible outcome? And then the second thing I was very interested in is you mentioned that shift where behaviors change after implementation. Like, is there, like, for the person who sends everyone for cath, for information to be fed back to them about outcomes, does that occur currently? Be an opportunity in this project where now that you're seeing referral patterns, like similar to what's happening in family medicine, opioid prescribing, you now get on your prescribing patterns. Would that be a potential outcome here?
So you were glitching a little bit there, Samir, but I think I picked it up. JD, do you want to tackle first, and I can just add if there's any considerations?
Yeah, and I think parts that we're cutting out, I'm not sure, but if somebody is referred through this program and as part of the study, they would get one or the other test. Yes, there is the rare patient, just as there is in this day and age without the study, that if we don't think anything's appropriate or they've already had testing and they don't need to go further, then yes, everything could be canceled, but that would be less likely. I don't know if that answers your first part of the question.
And then, yeah, with respect to the opportunity for quality improvement, what's sort of been interesting is, in my work with JD, I've learned that there has been efforts to solve this problem through audit and feedback before, through chart reviews and letting clinicians know about that. So it's a bit of an open question about whether the behavior, like those audit and feedback, I don't think, right, JD, they haven't been super effective at solving this problem. So it's hard to say if this distribution shift is going to be real or not. So
yeah, no, it's a great question. They've been doing audit and feedback with the province for years, trying to improve this normal rate, and it's been on the radar of Core Health, and it's had the needle has not moved one bit with this. Now, that was not to the individual physicians. That was back to the centers to help try to deal with their data, and that's where CarDIA came out in the first place. The challenge with the individual refers, if you take a refer and you remove the acute referring or the acute patients, which wouldn't be part of this study, then the absolute number that they're referring in a given time period is very few patients. And then audit and feedback is less effective, where they can discount it, oh, well, this patient's different, this was different, and so on. And so it just doesn't have the effect. But we have thought about that, and it has been trialed in other centers without any kind of significant change in behaviors.
Okay.
Thanks for the question, Samir.
Thanks a lot, everyone. We are getting close to the time allotted for this rounds. I want to thank Dr. Petch and also JD for answering questions, for a very lively session. And thanks all the audience for joining us today. The next AI in Healthcare rounds will be on Wednesday, March 20th, with speaker Dr. Mark Cicero, co-founder and co-CEO of 16-Bit Incorporated. And then also to let you know that you will receive a request for evaluation. So there's going to be a QR code to complete an evaluation survey following today's session. We really welcome feedback. And thanks again, both to speakers and audience for a lively session. Thank you very much.
Thanks so much for having me. Take care.